What's up guys, welcome to this video. Today I will introduce a new concept which is called BST, binary search tree. So just like a binary tree we just talked about in my last video, binary search tree is just a special kind of binary tree. So just like the binary tree, it has most two children. And if we look at this example, so in this graph, this is an example of the BST. We can find that all the children's value of the left subtree, it's always smaller than the root value, and all the value of the right subtree are always bigger than the root value. So that's a second unique characteristic of the BST, which is, just like what I told, all value of the left subtree is smaller than root, and all value of the right subtree is bigger than root. And this still holds true for all its subtree. So if we look at this subtree, it still holds true, right? If we consider 10 as the root, 5 is the left subtree, left children, and 11 is the right child. So 5 is smaller than 10, and 11 is bigger than 10. So still holds true. Similarly, it also happens for the right subtree. Let's go through these three basic operations of BST. The three basic operations are find, insert, and delete. So we start from the find. On my right side, there's a BST. And if we want to find element 10, we will start from the root. We'll compare root with 10. So 10 is smaller than 12, which means that it will go on its left side. And then we go to its left children, and we find 10. So if we choose another example, like 48, so 48 is bigger than 12. So it's on its right side. 48 is still bigger than 24, so it's on its right side. So we find 48. So from these two examples, we can tell that if we want to find an element, usually it will take the number of levels. In other words, it's equal to its depths. So as we prove, usually the worst case will be ON because it could be line in a line. It could be the BST could only have the left children or right children. And if it's a balanced BST, on average, it will be log n or log n to find an element in a BST. Similarly, we have the same situation for insert. So if we want to insert an element like 8, we'll compare 8 with 12. So 8 is smaller than 12, so it will go to left. 8 is still smaller than 10, so we will implement 8 here. Okay. So if we want to implement like something like 26, for example, 26 is bigger than 12, so we go to 24. 26 is bigger than 24, so we go to 48, but 26 is smaller than 48. So 26 will be here. The worst case is ON, and the best case is log n. Not a best case, but on average it's log n. We'll have go to the delete. So we just like 10 as an example. So also 10 is smaller than 12, and we'll go to here. So we find a 10. We have two situations here, basically. One is called unbalanced BST. The second one is called balanced BST. So unbalanced ones look like something like this. So it is not a very good organized BST. It will reduce the efficiency of searching, deleting, and inserting. So we always want to find something like this, which is a balanced ones. So usually in BST, we want after insert or delete node, we will rebalance the BST. So we'll talk about this later. There is some legal question about this as well. For all of them, insert, delete, and find. For unbalanced situation, it's ON, so it's linear. For balanced ones, it's log n, which is much better in this case. So let's start going to implement a BST. I will start implementing it to demonstrate how it works in the code. So we'll continue writing the code at the implementation, insert, delete, and find of BST. So let's start with the node class. So node class usually was using to define what is stored in a single node. So in this case, we'll store one single value, which is the integer. Okay, so we're using int to store it, and it will return. So this is a constructor in the Python. So we'll assign a value to the value. And because this is BST, so we only have two children, which is left and right. Now we can just give them none. And then we want to define a new class called BST. So we will put all those three methods into this class. Each class needs a constructor, just like this. And now this time, we will use node to construct it. Okay, and then we will define some interface for this method. We can call it find. And we have insert, and also we have delete. So we'll start from find. So just like we were showing in the graph, if we want to find an element, like if we want to compare each node, right, with the value, we need to know like which node are we comparing right now. So we might need some helper function to help us to do it. So we want to define a helper function. So this means this is a private function. So in this case, we want to know which node are we using right now, and also we want to know which value are we comparing. If we're dealing with those like tree issues, we always start from the base case. The base case, usually it is empty tree case. So we will consider this node is empty, is none. So if this code is none, so we just return none. Okay. The second case is, because this is a recursive function, we want to know like how we terminate this method, this recursion. So this is the fourth case. This is something that apparently we didn't find a node, and we want to know how we can find a node. So usually what I will do is like imagine there's only one node, how we know it. So if it's one node, we just compare the node value equals to value, right? If it is true, then we just return the node. So that is the success use case. Okay. Then we'll need a recursion like some formula. So just like the BST, because we want to find the right element, the right node, and we know the value of the node. So we will need to compare the value with current node. If current node's value is larger than value, which means this value has to be on the left side of this node. Okay, so we will need to find at this left side. Otherwise, it will be on its right side. Then we can fill this method, helper method, into the interface. So we will just return self.find, and we will replace it with the root node. So here, I think we'll call it root. And now we will call it, the value will be the same. Okay. Similarly, we will do the same process for the insert. So we'll speed a little bit up. Oh, sorry. If node is none, what will happen? We can just give them a new node, which is contain only one value, which is the value we want to insert. Okay, so it's called value. Second use case is, suppose we want to insert. So we want to know like which part of it we can insert into. We cannot insert directly into the root, right? Because if it has left children or right children, do they disappear? No, they do not disappear. They have to be there, right? So we'll do something like adding this value until we find an empty place for this new value to be stayed. Okay, Let me write a code and I will explain what I mean. So just like BST, if node value is smaller than value, so it will be staying at the right side. So we will keep finding its right side. So we will find the right side and we'll give the value. Otherwise, if node value is larger than value, we'll go to its left side. Okay, so what does it mean? Let's get back to this graph. I will explain it. Suppose if we want to insert 8 by using our algorithm, so we'll know that it's 8. Suppose current node is the root, which is 12. So it's here, right? We know that it will go to its left. So we will modify its left. This left will no longer be current left. It will be a new left node with this new value 8. However, we don't know which place this 8 should be best fit. So we continue searching. Since this is recursively, it will go to its left, and left still is bigger, 10 is still bigger than 8. Okay, so we go to 10's left. So current node becomes 10, and 10 is still bigger than 8. So we let it go to its 10's left children, which is none. Okay, current node becomes the empty tree, which is none. And then we can go back to our code. And because it's none, it will be replaced with a new node called 8. And what happened is, in the graph, it will look like something like this. That's how the code works. Let's get back to the code part. So I explain why this looks like this. And the last case is node's value equals to the value. What will happen? We will do nothing. We don't need to insert, it's already there. We just need to return the node. So let's fill in this part. So similarly for the delete, okay, we will still use a helper function to help us delete the node from the BST. Okay, so we always start from the empty case. So if non node, we just return none because there's no node to be deleted. And also because it's the BST, so we know that if the node value is larger than value, it's on its left side. So we'll just do something like this. It will be similar to the insert. Okay, now if node value is more than value, it will be on its right side. So self.delete is node right value. Okay. However, there's one very complicated situation here. If current node is the value we want to delete, what will be going on? What will be the scenario here? Let's go to the graph to see what will happening. So suppose right now, if this node is, for example, 7, okay, so it will be very easy because it doesn't have any children. We can just remove it. That's done, right? And this one will assign to none. Okay, so nothing will be changed. However, what if that it still has another child? Okay, which the value may be 5, for example. What will happen? So this is the left child of the 7. So 7 will be removed. So this 5 will become the children of which? Of 10, right? So even 7 is deleted, we still need to take care of this child. And suppose this is not its left child, but its right child. Okay, what happened? The same thing, right? We need to take care of it. So for example, this is 8. We need to let the 8 becomes the left child of 10. So this one's removed, but this one will be still exists in the BST. So how are we going to write the code? So if we want to write a code to demonstrate this issue is, so it will become another else. So this is when node value equals to, okay. So we will know that if current node, So if current node doesn't have left, so we will return its right subtree. Same thing, if node right subtree is none, we'll return its left subtree. If it's both are none, it doesn't really matter which one return is none as well. So that's covered this use case. However, this one situation that's more complicated. So if they have both left and right, what's going on there? Let's go back to the graph. So in this graph, what if we're trying to delete 12? Okay. That's a very hard decision. If we want to delete 12, okay, so it's gone. Should we make 10 or should we which will be the new root, right? That's a new question. That's a question that we don't know. So in that case, there's a strategy. We can keep one part, like either right or left subtree, unchanged. Okay, that's the strategy we have. So how does it work? We will, for example, so this one, we'll just example here. We'll keep the left side unchanged. So this will keep its original look. So we will find a successor from the right subtree. We'll find a node in the right subtree to become the new root. Which node should be selected to be new root? Usually, we will select the smallest node from the right subtree to become the new root. So why does it work? Okay, so we want to select something that it doesn't have any children, which is a leaf. So in that case, we don't need to care about children issue. You know, that's what makes problem much easier. So in this case, we'll select 20 to be this new root. Okay, so 20 will going to be the new root. Does it make sense? Does it still hold the property of the BST? Yes, it does. Why? Because 20 used to be at the right side, right subtree, right? So by its property, it must be bigger than every value on the left subtree, right? And also, because it's the smallest value, everything on the right subtree will be bigger than it, right? It still holds true. So that's why that's the strategy we want to use. And the benefits is also, we don't need to care about its children because it doesn't have any children. It's the leaf. It's the smallest value, smallest node on the right side. Okay, so that's a strategy we'll use to delete a new node from the BST. So how we achieve it in the code? Okay, since we want to find the smallest value, so we can have some another helpful function to help us find it. It's called find smallest node. Given node, we'll just keep finding the nodes left. Okay, so in the code, we'll do something like this. Find the smallest element from right subtree of node. Okay, equals, using the helper function we just defined. Okay, and we want from the right subtree. We want to replace just the value and keep the relation of left and right to be the same. So how we do that? We just replace the value of it. Okay, and the last thing is we have to delete the smallest element from the right subtree because it doesn't exist anymore. It moved to the top, moved to the root. Voila! So we have done everything right now. Okay, and at last we'll return the node. Okay, so now we want to test our functionality, whether BST works. So we will still need some helper function to help us to know whether this tree is printed in correct order. So we'll use something called in-order traversal. So what is in-order traversal? Let me write a code first and I will explain in graph what is it. So we'll just call it traversal and we'll take a node as current node and we'll have a result. So this result is an array. It would have an order of the node's value in it. So it will check we will check whether node exists. And then we will first append the left subtree into this array. So we will call traversal again. However, this time we'll call it to the left child and result. And then we'll append our current value, which is node of value. And then last we'll append the right value of it. And then I will call it, so this is the private one, I will call it, maybe calling order traversal. So basically we'll need a result, and we will just self dot let a traversal. And we'll have the root as start point and result as and return result. Okay, what is it? So pretty much this is something we will talk about in the next tutorial. We just borrow it. So we have an in order traversal. What does it look like? Basically it is left to the root to the right. So in this graph, basically it was follow this pattern. So it's always from left, the leftmost, to its root and to its right. So in this graph it will be 7, 8, because this is the leftmost, right? Root and right, and go to this root and right, 10, 11, and go to this root, which is 20, and it was next one is 24, and it's 48. And so we can see that it's very interesting that it is in order. It's from the least to the most, smallest to the largest. Okay, so let's get back to the code. So we'll first create a BST class, and then we will insert each one of them. The order doesn't really matter because it is a BST. It will organize by itself. No matter which one you insert first, at last it will become a valid BST. So we can just insert in any order, like 48, 24, 20, 11, 8. So in that case, we have everything we want, and we just put in order traversal, and let's have a check. It seems good to me. And if we move delete 10, so if we want to delete, for example, we could delete 20 and see what's going on there. So if we delete 20, what is the expected value of it? So if we delete 20, by the algorithm, we would go to its right subtree, if it's 24 and 48. Okay, and we'll check whether it has left children. The first node that doesn't have left children will be selected as the root. So 24 will be the first one because he doesn't have any left child. And what happens, like this one will move here, and only the right side will only have a 48. Okay, let's check. If we test the BST, we'll see that it makes sense to me because 20 has been removed. It seems correct. So we also want to test the find functionality. So the 20 should not be there anymore. So it should return none. And if we check 48, it should return some node. Does that make sense? Yeah, it does make sense. Okay, I think that's the end of today's video. And today we have discussed the BST and the implementation in Python code of it. And thank you so much for watching my video, and click like if you really like it, and looking forward to seeing you guys in the next video.